So data converters are an important block in all sorts of electronic systems, especially since you are dealing with a lot of digital processing, but the world that's analog, right? I mean, the world that's still analog. So that interface is always there. And this has been subject of extensive discussion. So we'll do a very, very brief introduction to these data converters. And so we'll start with some of the definition and trying to make sure that we understand. So we start with a digital to analog converter, D2As, right? So what are the first thing what is an ideal D2A, a digital to analog converter, or D2A converter, sometimes shown as DAC, DAC. So what does an ideal digital to analog converter do? So it's a box that takes a digital word, right, n bits, width of n bits, and then it produces an analog output, right, V out. And the relationship between this V out and, so this is the digital to analog converter, the relationship between V out and the digital word input in is that you essentially have some sort of a voltage or some reference that gets scaled by the ratio of the digital word to 2 to the power of n. So this is like an n-bit converter, right? So it looks at the value of, let's say there are n bits. This is like a 10-bit, 8-bit converter. It means that you provide a digital bit, and it converts, you look at the value of that digital bit, and it's compared to whatever that 2 to the n is. So for example, if you have an 8-bit system, this is going to be 256. So if you provide a binary 1, you would get 1 over 556 of whatever your reference voltage is. So there's some sort of a reference voltage that gets scaled often in these things. So it's basically that reference that gets scaled. So an ideal digital to analog converter, of course, would produce an analog output. So if you look at the V out versus D in, it would be a change. So let's say you start from 0 and then you go up. So you have the, let's say it's 3 bits. So this is 0, 0, 0. And then for 0, 0, 1, you produce that. For 0, 0, 0, 1, 0, you produce that. 0, 1, 1, and so on and so forth, right? Till you get to 1, 1, 1. So you take a digital word and convert it to an analog voltage. Now, the input can be represented in various different ways, right? I mean, so one is a decimal or hexadecimal, things of that sort. But when you're dealing with bits, you're dealing really with binary. So for binary inputs, there are really 2 prominent ways of representing it in this kind of systems. One is the actual binary, right? Where you basically, let's say for 2 bits, so you have 0, 0, let's say 0, 1, 1, 0, and 1, 1. And then there's another variation which is called the thermometer code. Now, what is the thermometer code? Thermometer code is something that just is more redundant. And when you can think about it, I'm going to write it vertically. So the thermometer code for this thing looks like that. So it's like something that fills up, like a thermometer, the old mercury thermometer or whatever I just like. So it fills up like that. And it's useful in a lot of applications, as you will see when you're implementing these things, both in digital to analog and analog to digital. A lot of times it's easier, not always, but a lot of times it's easier to work with the thermometer code than the binary. And there are converters of binary to thermometer code converter, and it's a digital block. It's a combinatorial logic. And to thermometer code to binary converter. So an ideal D2A, if you think about the transfer function between the digital word, again, the same thing, plotted differently, you are looking at a variation that would happen at LSB, the half LSB, and then you, for every LSB that you go up, there would be an equal amount of change in the analog voltage, right? So this is what an ideal thing would look like. These steps are obviously fixed because all they're digital. And these steps are ideally all the same, the vertical steps. And they're all happening at the same location. So that's what an ideal D2A should do. Now, a realistic D2A doesn't do that. I mean, I tried to do this as cleanly as I could. Obviously, I didn't completely succeed. But what does a non-ideal D2A do? How does it look like? Well, the non-ideal D2A may already produce a voltage that's even when it's the input is 0, right? This is what we call an offset. So from that point on, the vertical steps may not be exactly equal. So you go, I mean, these things still have to happen at the same place, right? Because these are digital. The transitions need to happen at the same place. But, you know, it can jump up a small jump, a big jump, a big jump, another big jump, another big jump, small jump, small jump, small jump. Whatever. Well, I missed the transition point, but anyway, that's something like that. So there are quantities that are used to quantify these non-idealities, right? Offset is one, of course, right? So what else should we worry about? Let's think about what are the parameters and how should we define them. If you were to define parameters that quantify what kind of deviations you have from the ideal scenario. So you can see that this is not good, right? That some of the steps are big, some of the steps are small. Actually, even in some scenarios, you can even have a situation where this happens, right? It can become non-monotonic. So how can we come up with measures to capture these non-idealities in a few numbers that are general and easy to define and easy to capture? Things like that. So there are a couple of things we are worried about, right? One is if these steps sometimes become too large and sometimes become too small, right? That's a bad thing. So one of the things we care about is that how much does this deviate from the ideal jump, which is 1 LSB, right? So it has to jump by whatever, the reference divided by 2 to the power of n. This is the ideal delta here, right? So the deviation from that is important. So if you can look at the entire thing, say, well, the maximum deviation I can have in worst case scenario is x. That would be a useful quantity to know, right? That's some sort of a nonlinearity. We call that the differential nonlinearity, or DNL, because it's the difference between two adjacent points, right? So the differential nonlinearity. So for example, in this example, you have large DNL here, because this is in excess. If this was your delta, this is in excess of delta, so this is DNL. And then here we have a pretty large DNL because we should have been there, and now we are here. So this is the DNL, right? Now, and with that, you can say, and you can say, well, the maximum DNL or expected DNL, you can quantify your A to D or D2A, say, well, I want it to have a DNL no more than half an LSB or 1 LSB, and it's measured in units of LSB, right? Which is this delta right now. Now, does that capture everything? Does that capture all sorts of bad things? So if DNL is large, of course, you have this kind of problems. But is there another way things can break down that is not captured by large DNL, but it would not be very good?
Sort of
cumulative offset, right? So what happens is that if this thing, so I'm going to redraw it. So if this were the ideal line, and I'm not going to show the steps, right? Now, if these things started going like this, so each one of the steps may be clean, a little bit off, right? Each one of them steps may be kind of like more or less a little bit off, but in aggregate, they can produce a lot of large deviation here, right? In this case, it would be here. I'll show it with a different color. This deviation. Now, if the other one is the differential nonlinearity, what do you think we should call this one? Integral nonlinearity, right? So this is called INL, integral nonlinearity. So they capture different things. One captures local deviations, What's the maximum local errors you can expect. And one captures the global error that you can expect, a deviation, large deviation, which may not be captured in individual steps, right? This is a death by 1,000 cuts, or 1,024 cuts if it's a 10-bit one. But, and then this is basically an instantaneous thing, right? So here's the other thing. Are these enough to capture everything? Is there another way that these things can go wrong? So offset captures this if this is deviating from that, right? If it's like just up or down by some amount. DNL captures how much deviation you have locally from each one of these ideal positions. And INL captures the global nonlinearity, how much it bows or deviates from the straight line. Is there something else that you need to capture? There's a fourth one that you need to really capture to capture this all these non-idealities rather accurately. You can have a situation that your gain is actually, the slope is different. Now, you could argue that part of that is captured by the INL, and that is true. But in general, this gain deviation is a different kind of, it's not a nonlinearity, right? It's just a different slope. So there are four things. So this is basically called, so you have to think about the DNL, INL, offset, and gain error. So this is the gain error, how much deviation you have from the ideal gain. So these four parameters really capture the essence of the general static behavior of a D2A or A to D, or data converter. And we talk about them and you try to calculate it and estimate it and things of that sort from time to time. Now, there are also dynamic measures, right, for how well a D2A measure works, right? So some of what, let's say for a D2A, what are some of the dynamic measures that matter? So let's say you're doing something and your output goes like this. So you have one level, one digital level, and then you go to a different digital level, and then you go to a different digital level, and things of this sort matter. So what are some of the things that matter in terms of qualifying this?
How much ringing you have?
Well, yes, but is there how do you quantify that? Correct. Ringing, it may not be ringing even, right? For example, it could operate, it could look like this. The output could go from one value to another value like that. That's also a possibility.
Some sort of stabilization time constant.
Yes, exactly. Stabilization time constant. So how do we do that?
It's like settling time.
Settling time, for example, right? You can say how long does it take for it to settle? Now, what value should it settle to? Where should we set our threshold for defining where's a good time constant, time for settling, right? In your mind, there's a logical value that it should settle to, right? What is that? What value should it settle to? So in other words, what is the width of the window? Or so from the how much deviation can you tolerate before you can say, well, it has fully settled?
Whatever our target resolution is.
Target resolution, right? LSB, least significant bit, divided by 2 really, because otherwise it can be confused. So this needs to settle to LSB over 2. And the settling time to LSB over 2 really determines what your real speed is, because you may say, I've made this great 16-bit D2A, but it takes, and it's really fast, because rise time is really fast, right? And you can say, well, it does this in like 10 nanoseconds. So it's a 100 megasample per second D2A. Not so. If it looks like this, the time it takes for you before you get to say, I have settled to the 16-bit resolution, it's going to be probably very long, because you need to resolve this to 1 over 2 to the power of 17 of the final value. So if it's an exponential settlement, you have to settle to 1 to the power of 17 of that value. So settling time to LSB does matter quite a bit. So that's the metric that you use. The other thing, what else would matter? What else? matter. So that kind of like, if you want to quantify it accurately in terms of speed, you have to really say, well, how long does it take for the output to settle to half an LSB? Right? That's one thing. The other thing, what else does matter for D2A? So this is kind of speed, right? The sampling rate. But there's something that relates to speed too, but it's not the sampling rate. If you think about it. Sampling rate basically tells you how many samples you can take per second. But there's something else that actually matters, and it trades differently with this. Any thoughts? The delay, the latency, right? The question of that, how long does it take for your results to come out? Right? Sometimes it may take a long time for certain kind of architectures. You may have very high sampling rate, right? You're sampling at 1 gigasample per second, but it takes it 1 microsecond to get the results. So the results you're getting now are from 1 microseconds ago. But you get 1 gigasamples of results at the output, but they're from 1 microseconds ago, right? Now, would that matter? Does that matter or does it not matter? It depends on the application. So give me 2 examples. Let's see if you can come up with examples of a case where it does matter and a case it doesn't matter. So whatever, pick an example. Start with anyone.
It might matter if you're trying to do a really fast feedback system.
Right. So if you're trying to have a feedback system through your digital system, right? Let's say you're trying to control an aircraft, right? Then you are trying to control things very rapidly by reading digital data, doing the processing, and doing and actuating some change, right? So then latency does matter. I mean, well, depending on what kind of dynamics you have, 1 microsecond may not matter. But if it were like 1 second, for example, then it may matter. So latency would matter in real-time applications, in the cases when you're trying to close the loop around something through a digital path. Right, which happens quite a lot. Now, when doesn't it matter? Give me an example of a case where it does not matter.
Maybe you're just like passively recording sensor data.
You're recording passively sensor data. You're recording audio and video for later use, right? You can do all sorts of things that you are just basically storing. Or doing telemetry, for example, right? I mean, if you are in orbit and you're measuring things that are like 36,000, let's say you are in geosynchronous orbit and you're measuring things that are 36,000 kilometers away, the speed of light itself would produce a fair amount of delay, good fraction of a second. So what is another like 10 microseconds added to that? Nothing, right? So those are the kind of things to think about when you're designing. And you will see when we talk about architectures, especially when we talk about the A to D architectures, that some architectures really exploit these trade-offs. Some of them have a higher sampling rate, higher latency, or you can change the complexity or the power consumption, and you can trade this thing with the architecture. So, but before we do that, there are some things that are very common to A to Ds and some questions of concept. So how do you generate, what is the simplest D2A we can make? Let's start with simplest architecture for a D2A. Let's make the simplest D2A we can make, and then we start from there, and then we continue to see, well, how we can improve it. Think about how can you make a D2A? Let's say you have resistors and switches, right? So how about if we have a resistive divider ladder? And you take your V reference and put it across a resistor ladder, a resistor branch, there's a bunch of series resistors. And you have resistors from R1, R2, R3, and they are same values, let's say, all the way to Rn, Rn minus 1, Rn minus 2, etc., etc. So if you look at the values of this thing, the voltages of these nodes, right? So the voltage on this node, what is the voltage on this node? Ideally, let's say they're all the same value. So let's say you tap off of these nodes. What is this? This is 0, right? If they're n, this is basically 1 divided by N resistors, so NR times Vref. So it's Vref divided by NR. And then this is Vref divided by 2 Vref divided by N, right? And this is Vref divided by N times 3, and so on and so forth. So this is basically Vref, and this is N minus 1 over N times Vref. I should have probably written it that way. That's a better way of writing it. 1 over N Vref, 2 over N Vref, 3 over N Vref. So somewhere in the middle, I have whatever the M is divided by N times Vref. So we have generated all the voltages that you can possibly want off of this ladder. So if you are making an 8-bit A to D, this has to be 256 resistors, by the way. So this N is really the capital N, which is basically 2 to the power of N. All of them. So if you're making a, let's say, you don't make D2As like 16-bit D2A like this, but if you were to make it, it won't work that if you do it that way. But anyway, you need 2 to the 16, 65,000 resistors, right, to do it this way. But now we don't have a D2A yet, right? We have a bunch of voltages. How do we make it a D2A? If you were to make a D2A out of this, very simple D2A. And then connect. How do we connect it? So, right? So that's a good question, right? So we need to switch it. We need to find a way to, at any point, let's say this is our output, connect one of these voltages to the output. And which one we connect is determined by the digital value, right? So you can, for example, have a situation where, let's say, you have a switch here. So let's say this is determined by B0, and this switch is connected at B0 bar. Right? And we repeat doing this every other stage, right? B0, B1, it's going to be B0, B0 bar. Because you remember, if the LSB, the lowest bit, is 0, you're either connected here, or you're connected here, you're connected here. You go every other one, right? This is not a great D2A, by the way, just what we're going to build. But just let's make the simplest D2A first, right? And then you keep going the same way. So you basically end up wherever, you know, this is the even. So this should be here like that. B0 bar, B0, and so on and so forth. So you have all of these. So the effect of the first bit is captured here. So you connect to the right one for the first bit, the LSB, the least significant bit. Then what's the next step? B1. Then B1. How do we deal with B1? Well, if B1 is 0, you're in this range. You're using one of these two. If B1 is 1, you're using one of these two, right? So you do the same trick here. So you say B1 bar and B1. And the same deal here. So this is going to be B1. And there's some sort of a B1 bar coming from the lower branch. That's starting from here. And then you connect that to the output. And so on and so forth. So you get B2, B3. It's a binary tree, right? At the end, you get a V out this way. The good thing about it is that you're actually doing your binary conversion to a thermometer code directly right there. Because what you're generating really is a thermometer code of the resistors, right? You essentially, the question is, where do I tap? The thermometer code will determine where to do the tapping. But I'm doing the binary to thermometer conversion right here with this. So that's fine. That's good. But so what are the problems? What are the challenges with this thing? Can you think of challenges with using this as a D2A? Yes?
Trading output impedance and power consumption.
Trading output impedance and power consumption. Great. So tell us more about, let's talk about the output impedance. What's the problem with the output impedance? You're right. So let's say you're trying to charge and discharge a capacitor. Here. Let's say your load is a capacitor, which can be the input of a MOSFET, let's say, of an amplifier or whatever. So if you're charging that, what is the problem? Think about it. Depending on what the value of bit is, you're connected to different parts of this resistive ladder. So you see different resistance, first of all. So your source resistance is different, right? So your time constant is dependent on the value of the bit, first of all. The other thing is that even if it were not dependent on that, if you're somewhere in the middle, you have a bunch of resistors. You have a large time constant, plus all the series resistance of the switches. You have n lowercase n switches in series, right, where you're connecting. So you have a fair amount of resistance. You're discharging things and charging through this thing, through this large resistor. You're charging and discharging this capacitor. So yeah, I mean, if you were really kind of trying to make it quick and dirty D2A, yes, this does work. So you know at least one D2A, but it's not the best D2A. Right? Any other problems you can observe with this, or notice, or you want to point out?
It generally seems inefficient to use 2 to the n switches to deal with in bits.
Yes, it sounds inefficient to do that. I mean, sometimes we do it. Remember one thing. I mean, the basic mantra of integrated circuits is that the number of elements does not, by itself, is not limiting, right? For all intents and purposes, as long as you're doing analog or RF or nothing massive digital stuff, you have unlimited transistors. Nowadays, even for digital stuff, you have unlimited transistors as far as that's concerned, right? So the number is not by itself a problem. It is a problem that you have these things. But now the other question is that can you really make a ladder like this that has very good matching properties? And what do mismatches in this ladder correspond to if you have a linear ladder like this, right? Because we talked about INL and DNL. And let's do a simple example of that here, where we actually talk about this in a certain way. So let's say that you assume a linear gradient in the resistors. So let's say you stack these resistors in a certain way, and you have a linear gradient, which what that means is that Rj, the jth resistor, or let's say Ri, is going to be R plus I delta R, right? That's a linear gradient, right? The resistances are gradually increasing as you're going from the bottom to the top. So this is the smallest one. Each one of them has a little bit of delta added to it. Now, the voltage on the jth node or the ith node is going to be what? The voltage on that is going to, so let's say on the ith node, what is the voltage? It's a resistive divider, right? It's the sum of all the resistances underneath it divided by the sum of all the resistances, right? So the sum of the resistances underneath is the sum of I equals 1 to, well, I don't know, the index, I have to use a different index. Okay, J equals 1 to I minus 1 of R's, which is basically R plus J delta R, divided by J equals 1 to N minus 1 of R plus J delta R, right? So times Vref. So that's the voltage on the ith node. Now you can actually write these things in that you realize that this part is just NJRs or IRs, I times R. Now this should be from 0 actually because you have the 0th resistor, R0 or R. If you call it R1, okay, so if it's R1, doesn't matter, then it becomes to I. Now, if you basically have that sum, you have I times R plus I times I minus 1. So it's the sum of delta R, 2 delta R, 3 delta R's, et cetera. That's arithmetic sum times delta R. Divided by N R plus N times N minus 1. In this case, it would be N plus 1, actually. This would be plus 1. Divided by 2 delta R. Times Vref. Okay. Now, and if you have this, then ideal voltage at the tap I, so ideally, Vi should be I over N times Vref. Now, what we are trying to calculate is a deviation from that. So if you want to calculate the deviation from that, for example, you can think about the INL, right? The INL at tap I is going to be VI ideal minus VI actual, which is this. And when you do that, what you get is you can just basically just plug this in. And what you get is I times n minus I divided by R plus n minus 1 over 2 delta R times delta R over 2n times Vref. So this is the INL, the deviation from the straight line curve that you will get because of this gradient, right? So it's this deviation at every point. Now you want to find the maximum INL. You want to find the maximum of this quantity. For what is the I for which this is maximized? And you can easily see it, right, from this term. It's n over 2, right? So because you can see at the two ends, it kind of like matches again, and it deviates, the deviation is maximum. So when you plug, so maximum for max for I equals n over 2. And then if you use that, then you will get the INL max of n times delta R over 8R. So what that tells you is that you basically, the deviation, the gradient, a gradient would produce an INL that's proportional to the rate of the gradient, right? The rate of increase. So you can see that the gradient does induce an INL. It does exactly this. Because at the two ends, you are getting, on one end you're getting to Vref, and on the other end you're getting to 0. So the two ends are tied. So that produces an INL. Now, how about DNL? DNL is relatively straightforward to calculate. So DNL is essentially Vj. So for DNL, you have the Vi plus 1 minus Vi, right? And if you calculate it minus the ideal, the step, the delta that you need to have anyway, which is Vref divided by n, and then you calculate that, that becomes roughly the maximum for it. So it is given by I minus n minus 1 divided by 2 times delta R over R. It's a straightforward calculation. Vref divided by n, and it's maximized, you can see, at the two ends now, at I equals 1 or I equals n. And the maximum value is going to be, so DNL max is going to be Vref times delta R over 2R. So if you have purely deterministic, well, not deterministic, purely predictable linear gradient, then your INL deviation maximum INL is this. Now, you can also get INL because of random fluctuations, because these resistors will not come out exactly what you expect them. So this does not capture that. If you have that, then you have to take that into account separately. You can say, okay, what is the maximum deviation of this guy, each one of them, and assume that they're going in two opposite directions, two of them, and see what maximum INL that produces. Maximum DNL that produces, differential nonlinearity. So these things can be quantified, and some of this analysis is helpful for the discussion related to choice of architecture. So this really trivial basic architecture that we have has these problems, and we know how it behaves. So what we'll do next time is to take this and start from this and then kind of go into other architectures and expand into more practical, more sophisticated architectures of D2As, and then go and talk about A to Ds. Okay. Any questions? All right.